In the video clip above, we talked about projection, what it means to take a vector y and project it into the same direction as a vector x, given by either a vector x itself, or we saw also all we needed was the x hat to give that direction. Now we are going to talk about orthogonal projection, which is the same kind of a concept, but it's the other side of the concept. Here, if we have a vector, this is coming up to be y. This is the vector y, and then this is the x hat vector. We just talked about what this one down here is, p x hat y. And we talked about how this is constructed so that that is a right angle. And it used cosine of theta, which would be this angle between them and everything. So that's what we call the component of y into the x direction. Orthogonal projection is the other side of this triangle. If this side plus then going up this side equals y, then to solve for this last side, it's y minus the projection of y. And so we have this formula that p perpendicular, or p orthogonal, that matrix is I minus p. Now, on the handout, you can go and prove for yourself that if we take the vector y and project it into the component in the x direction, and then project that into the orthogonal direction, though that double projection, projecting down this way, but then taking this result and projecting it into only the vertical component, would leave you with 0. We call that annihilation, actually. And so there are some steps there. Notice that it uses that idempotent property. See if you can reason your way through the steps of that p times p orthogonal equals, and then all the way to the other side of the equation equals 0. The other proof that you should work out for yourself, and the steps are shown, you just need to see if you can find for yourself the reasons, would be that if we take this p perpendicular, or p orthogonal, the I minus p, and square it, we should get the same thing itself. That's the idempotent property again. So p, the p matrix, has that property that this matrix squared is itself. This matrix here, I minus p, has the same property that squaring it or multiplying it by itself gives the same thing that you start with itself. So all of this is to give this result that we can take a vector y and we can decompose it into the x hat component, the projection onto x hat, and then adding to that the orthogonal projection, or the projection to the orthogonal complement of x hat.